This video is going to look at using implicit differentiation involving the natural log. If you remember, we talked about implicit differentiation before, and that's where we have our equation is not solved for y, it's mixed in with x and y. And remember, when we take the derivative, we have to look at using the chain rule or including when we take the derivative of y. Because here we're taking the derivative, remember, with respect to x. So if we're taking the derivative here, we're taking the derivative of d dx, which means we want to take the derivative with respect to x. So as long as our variable matches up, we're okay. But when we take the derivative of y, remember that's when we're going to take the derivative of y, but then we have to multiply that by dy dx, or we sometimes used y prime. And that's because y, we know, is representing a function of x. Okay, so let's look at an example here. The natural log of xy plus 5x equals 30. And to start out, the first thing we probably want to do is rewrite this again because we have multiplication. So instead of leaving this as the ln of xy and taking the derivative, we would end up using the product rule. We can split this to the natural log of x plus the natural log of y plus 5x equals 30. So now when we go to take the derivative, it'll be a little bit easier for us. And realize we're taking the derivative with respect to x. So we're taking the derivative of both sides of the equation. So ln of x, that means we're going to take u, which is x. So the derivative of x is 1, and that's 1 over u, which is x. So we get 1 over x plus ln of y. Well, our y is our u, and the derivative of y is 1, and that would be over y, so that's 1 over our u. But remember, we have to use like the chain rule here, so then we're going to multiply this by dy dx. So this is taking the derivative of y. We know y is a function of x, so then it's dy dx. And then we have plus 5x, and the derivative there is matching with our variable x, so it's just simply going to be 5. And of course, the other side, the derivative of a constant, is equal to 0. So now remember, with the implicit differentiation, now we are trying to solve for dy dx. And if it makes it easier, you can always go through and rewrite this. If we wanted to, we could think of this as 1 over y. Instead of dy dx, we could write that as y prime if you prefer. And we want to move everything else to the other side, so we would get minus 1 over x minus 5, because remember, we're trying to solve for the dy dx, which is now our y prime. That's a short way to write dy dx. And now if we solve for y prime, we need to get rid of 1 over y, so we can certainly just multiply both sides of the equation by y. So we'd be left with y prime equals negative y over x minus 5y. And there's our derivative. So this is either y prime equals, or you can think of this as dy dx. This is the derivative of y with respect to x, and this is equal to negative y over x minus 5y. All right, we have another example. 4xy plus the natural log of x squared y equals 7. And once again, we may want to rewrite this because we have the ln x squared y. We could certainly leave it in this form and take the derivative, but I'm going to think of this as 4xy. Now, we can't split up the xy here because there's no natural log, but the natural log of x squared y, we can write this as the ln of x squared, and the multiplication becomes addition, so that's plus ln of y equals 7. Okay, so now we're at the point where we can take the derivative, and if we're going to take the derivative of both sides, again, we're going to take the derivative, make sure I emphasize this, it's going to be d dx. We're taking the derivative with respect to x. Now for 4xy, we're going to have to use the product rule, and I'm going to group this as 4x multiplied by y. I'm going to group the 4 with the x, and that means the product rule says we're going to write the first term, which is 4x, and that's going to be multiplied by the derivative of the second term y, and the derivative of y would be 1, or simply 1 dy dx. And then the rest of the product rule says plus, we're going to take the second term, which is y, multiplied by the derivative of 4x, which would be 4. Okay, so there's the derivative of 4xy using the product rule. So then we would have plus the derivative of ln x squared. Well, the derivative of x squared would be 2x over x squared. Okay, so that's du over u. And then we have plus ln of y. So the derivative of y, that's our du. So the derivative of y, again, we're taking it with respect to x. So this would really become dy dx over our u value, which is y. And that's all equal to the derivative of 7, which is 0. So now we can go through and simplify, and it may be easier. I was trying to write this as dy dx to help you see this, but instead of dy dx, we could certainly write this as 4x y prime plus 4y plus 2x over x squared. That simplifies to 2 over x. And then we would have y prime. We could think of that as y prime over y equals 0. So we've already taken the derivative, and at this point we just want to simplify and solve for y prime. So to do that, the first step here, maybe to make things a little bit easier, is because we have 2 over x and this y prime over y, we could get rid of our fractions by simply multiplying both sides by the common denominator, which would be xy. And if we multiply both sides by xy, here we would end up with 4x squared y times y prime plus 4xy squared plus, now the x's cancel, so we're left with 2y plus the y's cancel, and you're left with x y prime equals, and of course multiplying by 0, that remains 0. So now we can group our our y prime terms. So here we have a y prime, and here we have a y prime. So we want to keep those terms on the left. So we would have 4x squared y prime plus x y prime, and then we're going to move everything else to the other side. So we would have a negative 4x y squared plus 2y, minus 2y. We want to subtract that over, so it's a minus 2y. Now, the reason for grouping our y primes together, we now can factor out the common factor of y prime. So we have 4x squared y plus x, and that's still equal to the negative 4x y squared minus 2y. And now the advantage is we can divide everything else away, so therefore we're left with y prime equals negative 4xy squared minus 2y, all divided by 4x squared y plus x. And we have our derivative with respect to x. All right, we have one more example, and this one is slightly different. Notice we do not have any natural logs in the equation, y equals x multiplied by the square root of x squared minus 1. And we have a little bit of direction here. It says we want to use logarithmic differentiation to find dy dx. Well, There's no logarithms here, but if we want to find the derivative here of y with respect to x, one way we could do this without the logarithm differentiation, we would have to use the product rule. We would have x times the square root of x squared minus 1, or we could think of this as x multiplied by x squared minus 1 raised to the 1/2 power. And another option is we can get away from the product rule if we think of this by taking the natural log of both sides of the equation. So if I take the natural log of y, and then I could take the natural log of x multiplied by the square root of x squared minus 1. So if we take the ln of both sides, then that allows us to think of this as the ln of y equals, well, this is all multiplication, x times the square root, because really we're taking the natural log of this whole piece. Well, with multiplication, remember, we can write that as addition, so that's the natural log of x plus the natural log of the square root. Well, we could think of that as x squared minus 1 to the 1/2 power. Okay, so if you notice here, we're trying to make things a little bit simpler for us to work with. Now, we could also simplify that even further because we have this raised to the 1/2. We could pull the 1/2 out front using our log properties, and you're just left with the x squared minus 1. So now we're ready to take the derivative. Well, keep in mind, we're trying to find the derivative of y with respect to x. So that means when we take the derivative of the natural log of y, the derivative of y would be 1 over y, but we still need to multiply that by our y, so that would be dy dx, and that's going to be equal to ln of x. Well, that simply is 1 over x. And then we have plus the 1/2 is just a constant multiplier, so we'll bring down the 1/2. And now we have the derivative of the ln of x squared minus 1. So derivative of ln again is du over u. So the derivative of x squared is simply 2x. And it's all divided by the x squared minus 1. So now all we have left to do is solve for dy dx. And maybe your first step here is to get rid of the 1 over y. So we could certainly just multiply both sides of the equation by y, and we would be left with dy dx, or if you prefer, you could think of this as y prime. And we would have, I'm just going to write this as y multiplied by 1 over x plus, and if we look at the 1/2 here, what happens? 1/2 and the 2, the 1/2 will cancel the 2 here on top. So there we're left with x over x squared minus 1. And there's our derivative. Now, if you notice the original problem up here, we had y equals x times the square root of x squared minus 1. And when we take the derivative here, notice our derivative is in terms of not only the variable x, but also the variable y. And there's really nothing wrong with this as an answer. Sometimes, though, you will see this written as dy dx. And then in place of the y, we know that y is actually equal to x times the square root of x squared minus 1. So we could write this then as dy dx equals, and substitute for the y, x times the square root of x squared minus 1, and then all of that's multiplied by 1 over x plus your x over x squared minus 1. So the advantage of this answer is, in order to find the derivative, all we need to know at a specific point is the x value. Whereas on the other side, we need to know not only the x, but also the y value. Now at this point here, we could come up with a common denominator, we could distribute the x times the square root of x squared minus 1. We could multiply that through, get a common denominator, combine things together. So you could do that if you wish. At this point, I'm just going to leave this as our answer. Okay, so there's a few more examples of taking the derivative using your natural log. And you may want to keep in mind of this technique here with this problem. Even if it doesn't tell you that you can use this logarithmic differentiation, if it looks like a problem you can use, you can always use this by taking the natural log of both sides and then simply rewriting your problem. And again, the advantage here is we could eliminate using the product rule.